Okay, so welcome to the second hour of session 7, essentially where we're talking about magnetostatics and matter. And I just want to go through another few things. I guess it's going to take me about 40 minutes. We'll see how we do. So what I want to start with today is a description of the field coming from a magnetized object. So the field of a magnetized object. Okay, so how do we want to proceed? Well, for a single dipole centered at some origin point r prime, what we had from last time was that the vector potential that's created at a evaluation point r is just mu0 over 4 pi, with now the dipole moment m that we saw last time crossed into, well, in this case it's going to be r minus r prime divided by r minus r prime cubed. Okay, so it's a 1 over r squared when you're measuring it at large distances. Okay, so let's now introduce a concept that will carry a kind of really surprising name, the magnetization. And this is going to have the symbol of capital M, so it's a vector quantity, and if it of course depends on a certain point r, as the density of dipole moments per unit volume. Okay. Okay, so here by density I mean per unit volume, right? Okay, so so in that case we can just rewrite for a magnetized object, yeah, that the total vector potential by the superposition principle is just the sum over all the contributions coming from all the little dipole moments that you have per unit volume. So it's going to be a volume integral of just what you expect, the magnetization at point r prime, crossed into our beloved r minus r prime as a vector, okay, scaled by the cube, so that it goes like 1 over r squared. Okay, so that's an extremely important equation. If you want, it gives you the vector potential coming from an arbitrary distribution of dipole moments. Okay, now written like this, once again, just like in the case of electrostatics, this is completely correct. There's no approximation in here, except for the fact that you're dealing with the dipole moments. But we can write this equation in a slightly more enlightening fashion by using some vector identities. Okay, so so let's find a kind of more enlightening representation Okay, we will once again use the identity that the r over r cubed is just the gradient of 1 over r. So what I'm going to write here is that the gradient with respect to the prime coordinates of 1 over r minus r prime is just what we need, right? So it's going to be the r minus r prime over r minus r prime cubed. Okay, so this is the same identity that we used before. Now we're going to use a product rule also. And what's the product rule? It's the product rule for the curl of a product of objects. So let's say I have the curl of a scalar function f times a vector function a. Okay, so this is one of the identities that you'll find in the cover of the book. You can quite easily rederive it for yourself if you don't trust me. So this is f times the curl of a, okay, minus a crossed into the gradient of f. Okay. So we're going to use that here. You see, so what we do is that we write a of r is equal to mu 0 over 4 pi, the integral over the volume d tau prime. I'm just rewriting the equation above, and now I have m at r prime, and I have the cross product into the gradient with prime coordinates of 1 over r minus r prime. Okay, if you want parentheses over this thing. So so you see this looks like this looks like this term here. So I can use this identity now to rewrite the integrand and then manipulate things a bit. Okay, so what I get is that the a at r is going to have a mu 0 over 4 pi. And now I'm going to give some big curly braces here. So what do I get? I get an integral over the volume d tau prime. And now you see I will have this term here. Now I have I'm just using this identity for the prime coordinates if you want. Okay, so what do I get? I get f, which f is 1 over r, a is just m, so I get the primed curl of m at r prime divided by r minus r prime. So that's the first term. And then the second term is that I just bring this one to the other side. So I get the integral over my volume, d tau prime, of the curl of the product of the f and a. So in our case, it's just m at r prime divided by r minus r prime. And then close the big curly braces. Okay, so once again, this is just a pure identity. We haven't made any approximations here. Okay, now there's a little thing that you can use for the second term here. So for the second term, we can use an identity and see a problem again 1.61 this time the B subpart in Griffiths. Okay, what does that tell you? That tells you that if you take the volume integral over a certain volume of the curl of a vector v, this is going to correspond to minus the surface integral of the vector crossed into the differential surface element. Okay, so this is a simple exercise that you can look at. It's just a relatively straightforward vector identity that you can check for yourself. So now what I can do is just use this in here, because you see now what I'm going to get is just that I'll have a surface integral instead of this volume integral here. So we can rewrite our vector potential A of r as a sum of two terms. So there's mu 0 over 4 pi. This is the first term completely unchanged, just as it is, d tau prime, and then the gradient with prime coordinates of m at r prime, and all of this divided by r minus r prime. Okay, and then the second term, I use this identity, so the minus sign goes from this. The second term becomes a surface integral. So the surface bounding the volume V of now the magnetization vector at r prime crossed into the surface element dA prime divided by, once again, r minus r prime. Okay, so this is quite a nice form here that again parallels a little bit what we did in the case of electrostatics. So we can give a reinterpretation for this formula. And the reinterpretation that we will give is as follows. We will say that the curl of the magnetization corresponds to some density of currents. Okay, so this is a bound current density. And this term here, the m crossed into the normal unit vector at the surface. Yeah, so again, you're used to this notation by now, I hope. Normal unit vector at the surface. What we're going to interpret this as is as a surface current density. Okay, a bound surface current density. So bound surface current density. Okay, and what that allows us to do is rewrite the vector potential as a sum of two contributions. The contribution coming from the bound currents in the volume, so J bound is a vector quantity at r prime divided by r minus r prime, plus a contribution coming from the surface currents. This on the surface, and then yeah, let's say let me write it like this. Yeah, so I have a surface differential element, but now I have the bound surface current density at r prime divided by r minus r prime. Okay, so what's the kind of magic behind this? Well, actually, it's a complete parallel to what we had in electrostatics. And the nice thing is that it's actually physically meaningful to talk about this. So if you have, say, a big volume that contains lots of circulating currents in it, okay, then, I mean, again, an impossible drawing for somebody like me. You see, the point is that the, let's start with this term here. Quite simply, the currents that you would get at the edge, you see, they wouldn't be compensated by their neighbors. So if you take one of the, let's imagine that the density of these dipole moments is uniform, then essentially there's always a cancellation because one side kind of goes against the other. So let's say that they're all uniform, then they cancel everywhere in the bulk, but at the boundary they don't cancel. So you maintain a kind of surface current coming from the bulk magnetic dipole moments that you have. That's this term here. Now, if the magnetization is not uniform inside the space here, then the internal cancellations don't quite happen perfectly, and you are left over with a certain, dipole moment density. So that's why the bulk bound current density is proportional to some derivatives of the internal magnetization of your object. Okay, so it's very much like in the electrostatic case, but now the concept's applied to the physical density of dipole moments. Okay, but really you can trust that this representation actually represents physically the things that are not cancelled from each other. Okay, so it's a real physical thing. Okay, there are quite a few nice examples in the book, so we can just very briefly discuss one. So example 6.1, which is the field of uniformly magnetized sphere. Okay, so let's imagine a sphere. Yes, okay, and the m vector inside of it, say, is a uniform vector along the z-axis. Okay, its value doesn't change throughout the sphere. So if we calculate the density of bound currents, when we take the curl of this m, well, it's just equal to 0, because m is a constant inside the sphere. Therefore everywhere inside the sphere, the bound currents are 0. The bound surface currents, however, don't vanish, because I've got here m crossed into n. Okay, and essentially, so m is along z, and n, you see, will change as I go here. So there's the theta, and you see, so the theta hat vector goes like this. The phi hat vector would kind of circle around like this. So when I take the z vector with now the theta vector like this, I get a phi. So this is m times the sine of theta, yeah, where theta is my angle. Let's say I kind of measure my my position here by the angle theta, and it goes along the phi direction, so phi hat. Okay, so so we had an earlier problem of a rotating sphere with uniform surface charge sigma, and this one had surface charge, surface current density, which was just sigma times v, and this is sigma with omega angular frequency r sine theta phi hat. So you see, it's the same problem, yeah. So same under the identification that sigma r omega is equal to r magnetization amplitude m. Okay, so so you can refer to example I think it was 511, which gives you that the magnetic field was equal to 2/3 mu 0. Okay, so the message here is that it's the same problem as before. If you have a sphere with a uniform magnetization throughout, then it's completely equivalent to a rotating spherical shell with surface charge density sigma. Yeah, provided you do the right identification between the actual magnetization and the surface charge density and the speed of rotation. Okay, so so this was the field inside the sphere, and outside it's a pure dipole. So it's a pure dipole with magnetization, dipole moment, magnetic dipole moment, 4/3 pi r cubed times the magnetization. Okay, so this is just a straightforward case, but it's a nice parallel that these two things are completely equivalent to each other. But I'll let you look into that in more detail. Okay, so yeah, I mean, so you can also look at the book. There are some reasonings about how you should interpret these magnetic fields inside matter, etc., etc. Microscopically, of course, it gets immensely complicated, but we're going to work, if you want, with like averages of these things that simplify things quite a lot. So let me actually start to a new page here. And again, in parallel to the electrostatic case, we're going to introduce some more handy quantities to work with than the, if you want, full magnetic field. You'll see there's an interesting combination with the magnetization that we can introduce. Okay, so this section is carries a kind of strange title, the auxiliary field H. Okay, so historically, it wasn't clear to people what the magnetic field was, what was causing it, and essentially what you needed to include in its description. Now we're going to do the following. So we're going to separate the internal current densities into free and bound parts. So if I write full current density J, I'm going to interpret this as being composed of two things. So first of all, the current density of bound currents and density of free currents. So the way you should understand this is that these things here, they come really from the actual matter that you're dealing with. So these might be atomic constituents that react to the presence of a magnetic field, etc. The free ones are really the ones that you plug in. So these are external fields that you would apply on the piece of matter with your, your bar magnet that you're holding in your hand. So let's just see why we want to do this. So we're going to start with Ampere's law. Which tells us that, so I'll write it like this, so 1 over mu 0, the curl of B. So what is this? Well, this is our current density. That's what Ampere tells us. But I will write this as the sum of these two things. So I've got the J bound plus the J free. But we've just defined the density of bound currents as the curl of the magnetization. Okay? So what we can do is just define a new object, H, which by definition will be 1 over mu 0 times B minus M. Okay, and this new field obeys the very simple relation that the curl, so its curl, is equal to the density of free currents. Okay, and this is like super important. Okay, so that's the differential form of it. You can also just write an integral form using Stokes. You just have the integral of h dotted into dl would be equal to the enclosed free currents, like this. Okay, where now this is just the integral over the surface of these free currents. Okay, the currents that go through, that pierce through the surface, defined by the the path that you have here. Okay, so so H here in magnetostatics is like D in electrostatics. Okay, you see it's just a convenient re-representation of the very same things, where we have isolated the external sources of currents for our fields. Okay, so very, very simple rewriting for this. Maybe I can do a tiny, very quick example. So in the book, there's example 6.2. And what's the idea here is that you have a copper rod of radius r, which carries, carrying a uniformly distributed current I inside its volume. Okay, so the question is really to find H everywhere. Okay, so this is quite simple. So what are we going to do? We're going to apply the integral form of Ampere. And what does that tell us? So we have our rod like this. Okay, that's the radius r that we have here. And now let's say we apply Ampere, and we just do a circle concentric on this rod here at radius s. So a circle of radius s. Okay, and I will write the s this way. Okay. So so for s less than r, what do we do? Well, we have the integral here, so the h is going to be just along this this vector here, this angular vector there. So h times 2 pi s, that would be the result of this integral here. This would have to be equal to the free enclosed current density, which is really the surface that we have, so just pi s squared, with the current. Okay, and it's the ratio between pi s squared and the total pi r squared. You see, so if s was equal to r, then the full current I would be done. Otherwise, you just take a chunk from the current. So what we get is that the field H is just, re-isolating it from here, it's just I times S divided by 2 pi r squared in the direction phi hat. if S is less than R. And otherwise, if you're outside, then you just saturate this thing, and it becomes just I over 2 pi S phi hat for S greater than R. And of course, at S is equal to R, the two things match. Okay, so so what happens is that outside, of course, the magnetization is 0, so you just get that the actual magnetic field is just mu 0 times H. Inside, inside, you get just the field H here. So of course here we know that the current is completely uniform. That'd be a thing, but in a general material we wouldn't know what the actual distribution of magnetization is. But still, the field H itself is very, very handy to compute. Okay, so that's just a very simple example of what you can do with this. Okay. Now, one little note of caution. We cannot assume that the magnetization that we have is divergenceless. Okay, so we can't say that this is equal to 0. Okay, it doesn't work. Why? Because really, if we calculate it, the divergence of H is just from the definition that we had, the divergence of B, and that we know it's 0, but the divergence of the magnetization is not necessarily 0. Okay, in particular at the surface of your material, there's no way that the divergence of the magnetization can be 0, because it kind of goes suddenly from one finite value to 0. Okay, and the right-hand side of this equation can be different than 0. Okay, so the H field is not divergenceless. So that's just one thing. You might get caught in some exercises if you think that that it is, like other magnetic fields. Okay, so just a couple of things. I'll postpone the discussion of energy in these systems until a later stage. Just to finish off, some notes on boundary conditions. Again, this parallels a discussion that we've done much before. So let me just state them, and you can check the book for the derivation, because it's quite straightforward. So if you have you remember how we did this? We were just doing little loop integrals around the surface, and now we just have different rules. Okay, so the statement of this thing is that you have a discontinuity in the H field coming from the free surface charge density. Okay, so this is really a complete parallel to the equations that we've already seen. Okay, so this is just the generalization of the ones that we have for the magnetic field, and again, I'll let you check the derivation of these things, because it's quite straightforward. I just want to end with some statements about linear and nonlinear media. Actually, we'll just make statements about linear media. Okay, so we're going to introduce just a little bit of symbolics here, which is really traditional in the literature. You've probably already seen these symbols in some places. So just some notes. If you have a para or a diamagnet, okay, so a diamagnet, I remind you, when you apply a magnetic field, then the magnetization goes against the field, so you reduce the effective field. In a paramagnet, it goes the other way. If you apply a magnetic field, then the magnetization kind of collaborates with it and increases it. Okay, but they both share a certain feature. If you set the B to 0, the magnetization disappears. Okay, and in many of these materials, so for small fields, what you'll find is that the magnetization is proportional to the field, okay, to the applied field. And the way this proportionality is usually denoted is that we write that the magnetization of an object is proportional to the field. Here I use field for H, times a constant chi m, which is known as the magnetic susceptibility. Magnetic susceptibility. Okay, so be careful because you know, there are mu zeros flying about. It's just a question of convention here. So this relation is characteristic of linear media. Of course, it's an approximation. If you have a real material and you apply some field, there will be a magnetization component appearing which is proportional to that, but if you want, there's a whole series of extra terms here that determine some nonlinear effects. The point is that most of the effects that you'll measure to a great accuracy will be linear to the field. Okay, so so in that case, what you can write is the following. So you know that B is equal to mu 0 times H plus M, just from the definition of H. And you can just write this as mu 0 times 1 plus the susceptibility times H. Okay? And that just means that you write B as another constant, which is mu times H. And this mu, so mu over mu 0, is just equal to 1 plus the susceptibility. Okay, and this mu is called the permeability. Permeability of the medium. Okay, so you know, this is just a set of special cases that we'll consider in many of the exercises. Once again, not all media are linear. Very often they've got some important nonlinear components. Actually, one of the most important examples of an utterly nonlinear medium is simply like iron. So iron can spontaneously magnetize. You would take a piece of iron and you would be able to measure a finite magnetization for it, even in the absence of a field. Yeah, so the external field is 0, but magnetization of the object is non-zero. So how nonlinear can you get? These things are called ferromagnets. So there's a whole zoology of different terms for magnetic materials. We'll maybe see a few of these things later on, but for now it's just the paramagnets, diamagnets. Ferromagnets we'll maybe work with a little bit later on. Okay, so so that's it for the short introduction to these things. Please refer to the book also for all the missing details to make sure that everything is clear in your mind. And we will start next week with actual dynamics in the whole setup. So we will kind of redo things a little bit in vacuum, but now including some time dependence. And after that, we will put everything back together until we achieve the kind of final formulation that we're looking for, which is the Maxwell equations in the presence of matter for full electrodynamics. Okay, so anyway, hope you're all doing well, and I'll talk to you again online next week. Thanks.